Welcome to this exploration of one of the most important papers in AI history. In 2012, Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton published ImageNet Classification with Deep Convolutional Neural Networks. This paper introduced AlexNet, a deep convolutional neural network that crushed the ImageNet competition and proved that deep learning was the future of computer vision. Before AlexNet, deep learning was a niche interest. After, it transformed AI. Let's understand this watershed moment. To appreciate AlexNet, we need to understand ImageNet. ImageNet, a dataset of 15 million labeled images across 22,000 categories. The challenge: classify 1.2 million training images into 1,000 categories. Report top 5 error rate. By 2011, best methods achieved around 26% top 5 error rate. Progress was incremental, a few percentage points per year. 2012, AlexNet achieved 15.3% top 5 error rate, a 10+ percentage point improvement. The competition was stunned. In 2011, computer vision relied on handcrafted features: SIFT, HOG, bag of visual words, SVMs. Progress was slow. Each new feature or classifier gave marginal gains. Deep learning existed, but was considered impractical for real-world images. AlexNet was a deep convolutional neural network. 5 convolutional layers, 3 fully connected layers, 60 million parameters, 8 layers total. Deeper than typical networks of the era. The architecture: Conv1, 96 kernels, 11 by 11, stride 4. Conv2, 256 kernels, 5 by 5. Conv3, 5, 384, 384, 256 kernels, 3 by 3. FC6, 7, 4096 neurons each. FC8, 1000 neurons. AlexNet introduced or popularized several techniques: ReLU activation, dropout, data augmentation, local response normalization, overlapping pooling. Each technique contributed to the breakthrough. ReLU activation, F-Gear Max, simple, fast, avoids vanishing gradients. Benefit: faster training. AlexNet trained 6 times faster with ReLU than Tang. Simplicity: just max. Trivial to compute. This simple change enabled training deeper networks. With 60 million parameters, AlexNet could easily memorize training data. Dropout solution: during training, randomly set 50% of neurons to 0. Effect: the network can't rely on any single neuron. Forces distributed representations. At test time, use all neurons but scale by 0.5. Dropout was the key regularization technique that made training such a large network possible. A crucial enabler: GPUs. The problem: training on 1.2 million images with 60 million parameters was computationally intense. The solution: NVIDIA GPUs, specifically GTX 580s with 3 GB RAM. Implementation: custom CUDA kernels for convolution. Split the network across 2 GPUs. Training time: 5-6 days on 2 GPUs. Without GPUs, training would have taken months on CPUs. AlexNet used aggressive data augmentation. At training time, random 224 by 224 crops from 256 by 256 images, horizontal flips, random color, lighting changes. At test time, 10 crops, average predictions. This effectively multiplied training data, reducing overfitting. AlexNet's performance was unprecedented. Top 5 error, 15.3%. Top 1 error, 37.5%. The gap: not marginal improvement, a dramatic leap. The computer vision community immediately recognized this was different. The 2012 competition changed everything. Second place, used traditional features. AlexNet learned features end to end. The lesson: deep learning could learn better features than experts could design. Within a year, nearly every top entry used deep convolutional networks. AlexNet succeeded due to a confluence of factors. 1. Scale. ImageNet was large enough to train deep networks without catastrophic overfitting. 2. Depth. 8 layers allowed learning hierarchical features. 3. GPUs made training computationally feasible. 4. Regularization. Dropout and augmentation prevented overfitting despite model size. 5. ReLU enabled faster training and deeper networks. 6. Craftsmanship. Careful implementation and hyperparameter tuning. Visualizing what AlexNet learned revealed: Layer 1, edge and color detectors. Middle layers, texture and pattern detectors. Higher layers, object part detectors. Final layers, object-specific neurons. The network discovered the feature hierarchy that vision researchers had been manually designing for decades. The three authors each became influential. Alex Krzyzewski, the primary implementer, created the CUDA kernels that made training possible. Ilya Sutskever, key contributor, later co-founded OpenAI, now leads Safe Superintelligence Inc. Jeffrey Hinton, the advisor, pioneer of deep learning, Turing Award winner. Together, they demonstrated that neural network ideas from the 1980s could finally work at scale. After AlexNet, 2013, ZFNet won ImageNet with refinements to AlexNet. 2014, VGG and GoogleNet pushed deeper. 2015, ResNet achieved superhuman performance. Today, vision transformers and other architectures dominate. The annual ImageNet error rate dropped from 26% to under 3% in just a few years. AlexNet's impact extended beyond classification, object detection. RCNN used AlexNet features for detection. Segmentation. Fully convolutional networks adapted the architecture. Transfer learning. AlexNet features useful for many tasks. Medical imaging. CNNs diagnose diseases from scans. Autonomous vehicles. Deep networks process camera inputs. AlexNet triggered an explosion. Academic neural network papers dominated conferences. Industry, Google, Facebook, Microsoft pivoted to deep learning. Investment, billions flowed into AI startups. Applications, face recognition, voice assistance, recommendation systems. Hardware, NVIDIA's GPU revenue soared. Custom AI chips emerged. The paper redefined what AI could do. AlexNet wasn't just incrementally better. Magnitude of improvement, 10 plus percentage points, not 1 or 2. New paradigm, learning features instead of designing them. Reproducibility, the techniques could be applied broadly. Scalability, showed that more data and compute helped. Generality, the same approach worked for many vision tasks. In 2018, Hinton, LeCun, and Bengio received the Turing Award for deep learning. The citation specifically mentioned ImageNet 2012. Their methods are now widely used throughout the research community and commercial organizations to achieve impressive results in a variety of problems. AlexNet was a pivotal demonstration that made the award inevitable. AlexNet teaches enduring lessons. Scale matters. Large datasets and models can overcome previous barriers. Simple ideas work. ReLU is trivially simple but transformative. Engineering matters. GPU implementation made the difference. Regularization enables. Dropout allowed training larger models. Data augmentation helps. Free performance from the data you have. ImageNet classification with deep convolutional neural networks is well organized. 1. Introduction and motivation. 2. Dataset description. 3. Architecture details. 4. Training methodology. 5. Results and comparisons. 6. Analysis of learned features. AlexNet was the culmination of decades of work. 1980s backpropagation, convolutional networks. 1990s, 2000s neural network winter. 2006, Hinton's deep belief networks renewed interest. 2009, GPUs used for neural networks. 2012, AlexNet proved deep learning works at scale. The ideas weren't entirely new, the scale and engineering were. ImageNet classification with deep convolutional neural networks is one of the most important AI papers ever written. Krzyzewski, Sutskever, and Hinton showed that deep convolutional neural networks trained on GPUs with large datasets and modern techniques could dramatically outperform traditional computer vision. The paper launched the deep learning revolution. It proved that scaling up neural networks, more layers, more data, more compute, produced unprecedented results. When you unlock your phone with face recognition, when image search finds what you're looking for, when cars see the road, you're benefiting from what AlexNet proved was possible. The gap between second place and AlexNet in 2012 was more than a competition result. It was a signal that AI had fundamentally changed.